Okay, so today we are going to do lecture 13. Which is going to be a continuation of things that we have done about vector spaces. So we talked about vector spaces, we talked about subspaces. So just for the sake of recalling, vector space has a structure with two operations, addition and multiplication by a scalar, and subspaces are vector spaces in their own right with the same two operations borrowed from their ambient vector space. Okay, we saw, so this is what we did last time. We saw that R2 has only the following subspaces. One was R2 itself, the other was the so-called zero subspace, and then we had a family of subspaces, which we said was lines passing through the origin. Okay, so these are the couple of things that we had seen. Now the question is, will such a structure hold true in R3, R4? And the answer is yes, those structures will hold true even in R3, R4. You will have only few subspaces. For example, in R3, these are the only subspaces we are going to have. So in R3, definitely you have R3 as a subspace, the zero as a subspace. Then you have lines passing through the origin and planes passing through the origin as subspaces. So these are the four subspaces of R3. Or I shouldn't say four subspaces, I should say four types of subspaces of R3. And the proof that we did for R2, you can just extend that proof for R3 also. So the idea is this will be a good exercise for you to try to set it up and try to write down a proof for R3 and see how it works. Okay, in general we can say that in Rn we will have these kind of subspaces, the zero subspace, Rn, lines, planes, hyperplanes and stuff like that. So we are going to kind of try to learn a little more about subspace before we go on to very special kind of subspaces that we are ultimately interested in. So let me focus my attention to R3. And what I'll do is, I'll write down a few subsets of R3 and try to figure out whether these are subspaces or not. So let me try it. Let me start with my first set. So here's my subset of R3 of all vectors B1, B2, B3 such that B1 is 0. So the first component is 0 and the other two components could be anything. Okay. Will this be, so will this be a subspace of R3 or not? Now, first of all, we should check that A is non-empty. One of the vectors that we have to kind of find out which lives in A, and there is one obvious vector, the zero vector. So the reason I chose 0 as an example is it kind of kills two birds with the same stone. First of all, I have shown you that it is non-empty. Secondly, if you remember, every subspace has to have the 0 vector. So in some sense, it's a kind of a trying to validate that this could possibly be a subspace, because if 0 does not live inside the subset, then there is no chance of it being a subspace. However, just because 0 lives in here doesn't mean it is a subspace. We'll have to go for closure and everything. So what we do is, we'll pick 2 vectors in A. So let us say I have one vector as 0, u1, u2, and my other vector is 0, v1, v2. And if I look at their sum, it turns out to be the sum is 0, u1 plus v1, u2 plus v2. And as we can see, the first component is 0, so this definitely belongs to A. So it is closed under the operation of addition. So we are one step closer to saying that it is a subspace. Okay, so let's try and see if it is really a subspace or not. So we have to talk about whether it is closed under multiplication by a scalar. So closure under multiplication. Okay. So what I do is, I pick an arbitrary real number, let me call it as C, and I pick a vector in my subset A, and then I talk about multiplying the vector by this scalar. So this will be C times 0, u1, u2. It is the same u that I am using from the previous argument. Using the scalar multiplication in R2, you get this. And since the first component is 0, that means this guy belongs to A, and hence it is closed under multiplication. So then we can conclude that A is a subspace of R3. Because we have shown it is non-empty, it is closed under addition, it is closed under multiplication. So it is a subspace of R3. In fact, we have proved that this is a subspace, but if somebody says, okay, what is the geometry of this subspace? How does it look like? Is it a line? Is it a plane? Definitely it is not entire R3, and for sure it is not just the 0 subspace. So if you look at this A, what I'll do is, let us consider a typical vector in A. 0, v1 and v2. Okay. Now can I split it like this? Can I write this guy as 0, 1, 0, v1 plus 0, 0, 1 times v2. If you remember, we used to write our solutions to system of linear equations in this kind of a format. Now, if we focus on this particular expression over here, isn't this a linear combination of 2 vectors? So it is a linear combination of 2 vectors. In fact, if you notice a little more, these vectors are 0, 1, 0 and 0, 0, 1. They're not multiples of each other. So, in fact, I can also say that these vectors are independent. What does this mean for us? It means I have 2 vectors which are independent, and all possible linear combinations of those 2 vectors are the things that sit inside this A. Since we are having 2 vectors, and if you recall the idea of a homogeneous solution, these 2 would act like the solutions to the homogeneous equation. So this is, the geometry of this thing would be a plane that is passing through the origin. So suppose the first component is marked along this axis. Let us say this is x, this is y, this is z, then this is the plane that we are talking about, the so-called yz plane, because the x component is 0. So it is a plane that passes through the origin, and as we had sort of said earlier, any plane that passes through the origin will be a subspace. So in some sense, it's more like a verification of what we already knew in a particular example. Okay. Now, moving from this, let us try to change the set and see if we can identify a few things. Say, for example, what if I made a slight change in this set? So what I'll do is I'll keep on naming them differently so that we will use the example so that at least I don't have to write it every time, same thing. But it will also convey to us how things change. So here's my second set. I'm calling that set as B. This time, I'm making a small change over here. I'm making a small change over here. And let me say that the first component will be 1. Okay? So let me say my first component is 1. Now, is B a vector, is B a subspace? Of R3. Now, there are various ways to approach this. Of course, I can say that B is non-empty. So definitely B is not empty because, for example, I will say that the vector 1, 0, 0 lives inside B. So definitely it is not empty. But what about closure under addition and subtraction, and multiplication? Of course, we can go and try to verify them. But is there a simpler way by which we can say something about B? In some sense, I'm already giving you a little bias towards what the answer would be, but there's a reason for it. Now, if you look at it, the first component is being forced to be 1. So we can definitely say that the vector 0, 0, 0 will not belong to the set B. And hence B cannot be a subspace. So the reason I chose this example is to make sure we understand that checking the existence of 0 vectors sometimes could help us in figuring out whether a subset is a subspace or not. So for example, if I put B1 to be any non-zero number, then any such plane will not pass through the origin, and hence it will be not a subspace. Okay, so let's try with another example and see what can we say about something like that. So let's try a slightly non-trivial example, and perhaps that can help us. Okay, how about this one? Let me have another subset. B1, B2, B3. So this time I want my first component to be greater than or equal to 0. Okay. Now observe that 0, 0, 0 definitely belongs to C. So it is non-empty, and at least the test with the 0 vector is also there. How about closure under addition? So let's try that. So suppose I have two vectors, U and V. Suppose I pick two vectors in C. Now, since these guys are vectors in C, we know something about them. We know that the first component of both these vectors must be greater than or equal to 0. So if I add the two vectors using the usual addition on R3, I will get u1 plus v1, u2 plus v2, and u3 plus v3. Now observe that u1 plus v1 will be greater than or equal to 0 because by our choice of u and v vectors, both individual components are greater than or equal to 0. So for sure it is closed under addition. So is it a subspace? Well, remember we also have to talk about multiplication. So let me pick a scalar this time. Let alpha be a scalar. I am avoiding C because I am using the set as C. So alpha times u would be alpha times u1, u2, u3 vector, which would be this, alpha u1, alpha u2, alpha 3. Now, for this guy to be inside the vector in the set C, we should ask ourselves a simple question: will alpha times u1 be always greater than or equal to 0? And as you can see, since I have a choice of alpha to be any real number, so if I pick, say, alpha was -1, in which case alpha times u1 would be negative, and because of which it is not closed under multiplication. Okay. So this is not actually a subspace because it is not closed under multiplication. Choosing this example was to make sure that so the reason for this example was to make sure that we understand things could pass pretty much every possible test, but then fail in some test. So these are kind of things that we have to be careful about. Now let me try to make it a little more general statement. My ultimate aim is to show you something by means of example, so that once we see a pattern, we will try to generalize it as best as we can. So far we have seen a plane that turned out to be a subspace. That plane was passing through the origin. And we saw that that plane, the way we identified that plane was because it could be spanned by two vectors. So I'm after a general result, but let us first deal with examples. Let me go with another set. Again in R3, same thing, a vector with certain conditions. So this time let me choose, say, B1 plus 2B2 minus B3 as 0. Okay. Now, is this a subspace or not? I leave the basic things for you to check whether it is empty or not. But let's see. Is 0, 0 inside D? Is 0, 0, 0 inside D? And the answer is yes, because if all the components are 0, this particular equation, B1 plus 2B2 minus B3 equal to 0 is satisfied. But how do we check closure? Okay, so this is going to be a bit tedious, but this is the procedure to verify if something is a subspace, or at least for now it is a procedure. So let U and V vectors belong to D. Suppose these two guys are in D. Now, this time we have to be careful. Being a member of D, it comes with some kind of a expectation. Not any three-dimensional vector is a member of B. In fact, only those three-dimensional vectors are a member of B which will satisfy this thing. So, because they both live inside D, that means we know we have certain expectations out of them, or at least their components. So we know that u1 plus 2u2 minus u3 must be 0. Likewise, v1 plus 2v2 minus v3 must be 0. So we know that these two equations should be true. Now we can discuss what will happen to the sum of these two vectors. Well, addition is not a big deal. We can add it up. Usual way. Now, to check whether this guy belongs to D, I have to verify whether these components will satisfy that equation or not. Okay. So question is, does u1 plus v1, the first component, minus 2 times u2 plus v2, the second component, plus minus the third component, which is u3 plus v3, does this guy equal to 0? Now, let us look at the left hand side. Can I rearrange the left hand side as u1 plus 2u2 minus u3 plus v1 plus 2v2 minus v3? But we already know that these two expressions are 0 because of the membership in D. So now we know that the components of the sum vector is also going to satisfy the same equation. Hence, it is closed under addition. Okay, now let's see closure under multiplication. So this time we'll again pick a scalar. We talk about this thing, u1, u2, u3. This guy gives me a new vector whose first component is alpha times u1, second is alpha times u2, and so on. Now observe that alpha u1 plus twice alpha u2 minus alpha u3. I can write this as alpha times u1 plus 2u2 minus u3, which I know is 0. So that means the new vector that I have got also satisfies the same condition, the condition that I talked about over here. So it satisfies the same condition as the membership requirement of the set P. Hence, D is a subspace. So we can now conclude that D is a subspace of R. Okay. So we have a way to verify or check whether something is a subspace or not. We can go through this thing. But I want to share with you something which is peculiar out here. It is sort of a common theme that has occurred in this example and a previous example that I had shown you. So let us try to pick on that common theme and see what are we after. So I want you to focus on the set D. I said those three-dimensional vectors live in D which satisfy this equation. Okay? Let us pick a vector in here. Say v1, 2v2, oh, sorry. v1, v2, and v3. Now, if you look at this particular equation, b1 plus 2b2 plus b3 equal to 0, can we say that this equation is a homogeneous equation? Right hand side being 0, it's a homogeneous equation. So anything which satisfies this, can we say it is a solution to the homogeneous system? And if you remember in the first example where b1 was 0, that too was a homogeneous system. So let's see. If we are given a homogeneous system like this, how do we write the solution? Remember, here is my system b1 plus 2b2 minus b3 equal to 0. Here is its augmented matrix, 1, 2, minus 1, and 0. Okay? So we have one free variable and we have two. I'm sorry. Let me switch the names. I wanted to say something. We have one pivot variable and we have two free variables. Remember, we express pivot in terms of free. So we can say b1 is minus 2b2 plus b3. Okay, so far so good. So let's see. Can we write it as minus 2b2 plus b3? This is b2 and this is b3. Can I split it and sort of write it in this manner? Okay, now what do we see over here? Can we say, again we have, this is a linear combination of two independent vectors. Why independent? It's easy to see. Whenever you have zeros in the coordinates, it kind of makes life very easy. These two guys are independent because this can't be a multiple of the other guy because of the placement of the zeros. So in a way, this is a simple way by which given two vectors, we can say that they're not multiples of each other. So these are two independent vectors. So what we are saying is anything which is spanned by two vectors seems to be a subspace. In the previous example also, the vectors were 1, 0, 0, 1, 0 and 0, 0, 1. So could it be that if I look at the span of bunch of vectors, whatever comes out of it, can I always say that it would be a subspace? And the answer to that is yes. That if I have a bunch of vectors and I consider it linear span, whatever that thing turns out to be, that will be a subspace. And I want that result because it just makes our life very easy. Suppose we had such a result, that a span of bunch of vectors is always a subspace. And wouldn't you agree that we wouldn't have to go through all these hoops? We could have just said, this thing is the span of two vectors, and hence it must be a subspace. So it is a very simple test, but it comes with a small price. The price is, can you write things as a span of bunch of vectors? With some practice, you would be able to do. So here's the theorem that we are after. Suppose I have a vector space. And suppose I have a set M of some bunch of vectors v1, v2, v3, vk. So suppose this guy is a subset of V. Then whatever is the span of this set, span of M, subspace. Okay. As you will see, the proof is now fairly straightforward since we have some experience with dealing with the subspace. So we'll see how the proof goes. But notice one thing I have not mentioned in the statement of the problem, in the statement of the theorem. Try to see what is something which is not mentioned over here. And you will see that the statement here is a bit more general than what pattern we were seeing. If you look at it, I never assumed that these vectors are linearly independent. That means the result is even true if the vectors were to be dependent. So we are making no assumptions about linear independence whatsoever, and still this would be true. Okay, just to recall, and also to make life easy, let me just give this guy some name. L instead of writing span of M every time. Span of M is basically the set of all possible linear combinations of vectors in M. Okay. So I don't want to write span M every time, so I'm just denoting it by the letter L. Now, if you look at a typical linear combination, it will look like what? C1, V1, C2, V2, CK, VK. This is what something that lives in the span of M will look like. Notice, if Ci is 0 for all I, then that means the 0 vector will belong to L. So at least I am guaranteed that the 0 vector is living in L. So not only it is not empty, in fact we have shown something which lives in L, and that thing happens to be 0. Now what we will do is we will pick up two vectors in L. So let U and W be two vectors in L, and let alpha be a real number. Okay. So first things first. Since U lives inside L, I can say that there must exist some scalars such that U can be written as C1 V1 plus C2 V2 plus CK VK. Okay. Likewise, there exist scalars, let me call them as D1, D2, such that W can be written as a linear combination of the vectors in M. Now notice, if I add these two guys, U plus W, then this would be simply adding these two linear combinations. And if we do it nicely enough, and And as you can see, this is a linear combination of these vectors v1 to vk. Hence, this guy lives inside L. So we have shown that if you take two vectors in the span of M, their sum will also be a linear combination and hence belongs to the span of M. Now the only thing left for us to figure out is, what about multiplication by a scalar? What if I consider alpha times u? So if I consider alpha times u, so it is alpha times this linear combination which is nothing but and as you can see, this is also a linear combination of the same vectors. So this thing definitely belongs to L. Hence, L is a subspace of V. Now, if you notice, of course, we didn't need linear independence at any stage of the proof. But if you notice, I have proved this thing for any vector space, be it R2, R3, be it the vector space of polynomials of certain degrees less than equal to something, be it this vector space of continuous functions. So no matter where you are, as long as it has a vector space structure, the theorem will work. And if I may sort of add a note over here, even though it's a little premature, as you know, the world around you is finite dimensional. Like when you say R2, you think of 2 dimensions. When you say R3, you think of 3 dimensions. But I never said anything about the dimension of the vector space. Officially, we don't even know what the heck dimension of a vector space is. But when we do, at that time, come back to this proof and see. Nowhere have I said that this proof will work only in finite dimensional vector spaces. That means this proof can work in infinite dimensional vector spaces as well. So whenever you do a proof, try to see what is the scope or the extent to which it can be used. And that tells you the strength of the theorem that you are dealing with. Okay. Now with this thing in mind, we can talk about many subspaces. So in fact, any subset that we will deal with, if we have to call it, or if we have to check it as a subspace, instead of going through the usual route, we'll try to see if it is possible to express that subset as a linear span of a bunch of vectors. If we can, then we are all set. So, in order to facilitate our understanding of things a little more, I introduce something called the fundamental subspaces associated with a matrix. Some people call it fundamental spaces, fundamental subspaces, it doesn't really matter. Okay. Now, there are 4 things that there are 4 spaces that we are interested in. One thing we will call it as the null space. null space of A. I will generally denote it by NA. The other thing we'll talk about is the so-called column space of A. Which I will generally denote by CA. And the third thing is the so-called row space of A. And as you could possibly guess, we call it RA. The fourth thing what I'll do is, I'll give you a name for it that will not show much of a importance, but later on I'll give you another name for this guy. I'll call it the null space of the A transpose. Sometimes this is also called the left null space. And you will see the reason of choosing the word left for it once we encounter what definition we are after. What is the definition of this? So these are four spaces associated with a given matrix. And once we know these spaces about a matrix, it pretty much gives you everything that is worth noting about a given matrix. Now, the way usually these things are introduced, they're introduced by definitions. Here you have a matrix. Here is a definition of null space. Deal with it. Here is a matrix. Here's a definition of column space. Just start doing your calculations. But I would rather have you go through a little bit extra in order to understand why these spaces are important and think about these spaces geometrically, and then you will see things become quite easy. So let me first give you the definitions of some of these subspaces. And then we will try to learn some geometry out of it also. So the first thing in point is the null space. So whenever the word null comes into mathematics, you are usually reminded of something to do with zero. And that is exactly the idea. Null space is nothing but is the solution set of the homogeneous system Ax equal to 0. Okay, so if you are given a matrix A, which is of size m by n, then the null space of that matrix would be all the solutions for that homogeneous equation. Now, it's all good to look at, but if you look at this matrix A, okay, if you look at this vector x, the size of this vector x would be n by 1, because then only you will have some multiplication. And whatever comes out of it, whatever vector b comes out of it, that guy will have size m by 1. Right? This is what we have learned in system of linear equations. So the right hand side 0 vector is m by 1, the left hand side solution vector x is n by 1. So can I not think of A as a function which takes a vector from Rn and maps it to some vector in Rn? So let us think of A not simply as a matrix. Think of A as a function. From Rn to Rn. Now what does a function do? It takes an input, it produces an output. So can we say this function A takes an input, which is a vector x, and gives you output, which is a vector b. So are we okay with this? If you look at this, this function is not just any function. It is a little peculiar function. This function is a bit peculiar. It has two properties. Just trying to think if this is the right time to introduce the properties or not. But okay, yeah, I think we can deal with it. Look at this A. Suppose I take two vectors x1 and x2 living inside Rn. And suppose A acts on these two vectors. So can we say by the linearity of matrix multiplication, we can write it as AX1 plus AX2. Likewise, can we say that if I take any scalar alpha multiplied by vector x, then I can pull out that scalar and get to this. These two properties are what we call as the properties of linearity. Okay. And any function which possesses these two properties, that means it takes the sum of two vectors and maps it to the sum of the images. It takes a scaled version of a vector and maps it to the scaled version of the image. These properties, whenever a function possesses this, we will call A as a linear transformation. So think of it as a special function which has these two properties. So it's a function from some space to some space, but it has two additional properties, the properties of linearity. Now, just to make ourselves a bit okay with all the things we have learned so far, you must be wondering, we were talking about a matrix, all of a sudden we are jumping to functions. But believe me, everything will come together after some time. So be patient, just keep your curiosity level high, and we will be able to understand most of it without too much of a problem. Now, first let me spend a little more time with this linearity business. So can you think of a function A from R1 to R1, which is linear? So I'll write down an example for you and see if you can move from there. X is equal to 0. Is it a linear function from R1 to R2? Well, it's a function, that means everything getting mapped to 0. So in terms of pictures, I can tell you that here are two copies of R1, here is 0. Anything out here is mapped to 0. Okay, so anything from R1 to R1, everything from here is going to 0. Is it linear? Well, you can check through the definitions and see what happens. If I pick two numbers x and y, then this guy gets mapped to 0, because everything is getting mapped to 0. Now if I look at ax and ay, both are getting mapped to 0, so their sum is getting mapped to 0. So this implies that a times x plus y is ax plus ay. Okay. You can check the second part also similarly that it works. So it is a linear function. Do we know of any other linear function from R1 to R1? How about ax is equal to x? Is it a linear function? How about ax is equal to 2x minus 5x square root of 2x? Are these all linear functions? You'll see any time I multiply x by a scalar, I get a linear function. In some sense, this should remind you of the geometry. All these things are straight lines that pass through the origin. So somehow that linearity has something to do with the straight line structure or planar structure. But for example, ax is equal to x squared. This is not a linear function. So it is not a linear transformation. As you can see, it won't satisfy those properties over there. Okay. Now, How about if do you know of any function from R1 to R2 which is linear? That means a number getting mapped to a vector. Maybe it's a bit too difficult right now. Let me make it simpler. Do we know of any function from R2 to R1 which is linear? So that means as an input, it will take a vector x, y, and as an output, it would map to a number. So for example, if I map it to x plus y, is it linear? Well, we don't know. We'll see. I'll verify one of these two properties. Let me verify the second property this time, just to show you how things are done. So if I take, I scale the version of my vector, apply my function a on it, and see what happens. So this is alpha x, alpha y. And this gets mapped to alpha x plus alpha y, which is alpha times x plus y, which is alpha times a of xy. So can we say that at least the second property has been verified? Now I leave for you to verify the first property and see how it goes. So here's an example of a linear function from R2 to R1. Now, there's one thing I want you to see, which is the whole crux of everything that we have done so far. I'm not proving anything, but I'm just trying to show you some pattern over here. If you look at this, can I say that this is simply a matrix multiplication like this? So can we say that a linear transformation, at least by this example, it seems to be nothing but a multiplication by a matrix? And that is the reason we are trying to intermingle everything. We are trying to see matrix not as a matrix, but as a function which has some special properties. Because every function which is linear, at some stage we will be able to prove that every linear function is basically can be represented by a matrix. And the action of a linear function is that of matrix multiplication. And every matrix multiplication is indeed nothing but a linear transformation. That is something I'm not going to prove now, because it requires a bit more practice and understanding of things which we don't have at this moment. But as long as you can take this picture in mind, that a matrix multiplication is nothing but a linear transformation, and a linear transformation is nothing but a matrix multiplication, I think we should all be doing good. I want you to notice something about this particular example. I want to see which vectors x, y map to 0. So you will say, well, anything, for example, if you look at 1 minus 1, it maps to 0. If you look at any vector a minus a, can I say this guy will map to 0 based on the function that we have? So there are a lot of vectors which map to 0. So in some sense, if you look at, I'll try to show you geometrically, this is something important worth noting. So in our example, I looked at a bunch of vectors which are mapping to 0. So here is R2. I looked at 1 minus 1, then I looked at all vectors which lie on this straight line. All these vectors which lie on this line, A minus A, they are all getting mapped to 0. Anything which lies on that line is getting mapped to 0. Now, this is what we call as our null space of my matrix A. All those guys which map to 0, all those vectors in Rn which map to the 0 vector in Rn, we will call them as the null space. So here's an alternate description of null space. Null space of A is all those vectors in Rn such that A maps V to the 0 vector of Rn. So this is this concept of a null space you will see many different places in math where you take something and then you map it to the 0 of your other set or other algebraic structure. And we always love to have this set because this set is very special and dear to us. In fact, there's another name for it. Sometimes it is also called the kernel of A. Kernel is a more popular word when it comes to algebraic settings, but many linear algebra authors also use the word kernel. Kernel basically means core. So knowing which things go to the 0 vector somehow tells you the core aspect of your function or your matrix. In fact, what I will say is a statement which will make no sense at this stage, but and maybe at some point of time when you will realize the statement, then you will see what I'm getting at. The reason this guy is called core, because knowing this guy pretty much tells you everything about a linear transformation. In fact, if I know the null space of this guy, then I can tell you where other vectors will map just based on my knowledge of the null space. I don't have to sweat too much. I'll have to work a little bit and I will be able to tell you where all the other vectors will go, just because I know the null space. So null space really is an important tool, and we will be able to figure things out from here. Now, is null space a subspace? Well, there are a bunch of ways to look at it. It is a solution set of this homogeneous system. And the way we write down solution set of homogeneous system, if you remember, the solution set is always written as a linear combination of vectors. And from the theorem we have proved, this definitely should be a subspace. That is one way. Another way to prove that it is subspace is using the idea of linear transformation. Okay? So let me show you that way of thinking so that we can understand why it is a subspace. So here is my question that I will answer. So why is the null space a subspace of Rn? I'm assuming that the matrix that I'm working with is an M by N matrix, M rows and N columns. Okay? Well, the answer to this, I've told you one way, I'll show you the other way. Well, if you look at the 0 vector, A of 0 will map to 0. If you think in terms of matrix multiplication, or if you think in terms of kernel, all those vectors which map to 0. So definitely 0 lives inside the null space. So if nothing else, you know that 0 vector will always map to the 0 vector. So as you can see, 0 vector here is going to map to the 0 vector over there. So that is definitely there. Now suppose I pick two vectors, u and v, which belong to the null space of A. This means what? A must be taking u and mapping it to the 0 vector, and A must be taking v and also mapping it to the 0 vector. Then A of u plus v, you see I am using the linearity of the transformation, will map to the 0 vector, and hence u plus v also lives inside the null space. Now let us pick v. By the linearity property, we will get that this maps to the 0 vector. So this implies u plus v also belongs to the null space of. So we have shown that if two vectors belong to the null space, then their sum vector also belongs to the null space. And at least from this example, you see that this guy, this is what we are calling as the null space. It's a line passing through the origin, and we already shown that all lines that pass through the origin will be a subspace. So at least we are heading in the right direction. Likewise, we can now show that any multiple of a vector living in the null space will still be living inside the null space. So if you scale something inside null space, you don't leave the null space, you still remain inside it. Okay. So suppose we pick some scalar, and suppose we have a vector from the null space of A. Then we want to talk about what will A do to this guy. So using the linearity property, we can say that this is alpha times AU, and AU, A maps U to the 0 vector, so it is alpha times the 0 vector. This is the 0 vector. This implies that any scaled version of U will also live inside the null space, and hence the null space is a subspace of Rn. So the idea is, if you view it as a function or if you view it as matrix multiplication, either way you can think about this proof. If you only know matrix multiplication, then the same proof will work. If you understand it as a linear transformation, then you are using the linearity property. So this is something that we will continue to investigate, finding the null space of a matrix. Once we have been able to do that, then we will talk about the column space, and on the other spaces. And then finally I will show you how the four spaces are related to each other and the story they tell.